So hello everyone, and first I want to thank the organizers for letting me speak here. And I want to tell you about a couple of works that we did in the last few years, and in which we want to compute the relativistic wide-loop galaxy bispectrum, and we've taken the first steps in that direction. So I want to start by motivating it. I mean, why do such a complex calculation? And the motivation is primordial non-Gaussianity. And we see here the primordial three-point function, which is what we call primordial non-Gaussianity, higher order correlation functions of the curvature fluctuation in so-called commuting gauge. And we want to measure this quantity because it has a lot of physical information. And of course, the three momenta have to form a closed triangle due to translational invariance. And moreover, this is symmetric under exchanges of the three momenta. So I can, if I assume scale invariance, I can plot all of this in this triangular region. And in this triangular region, there are several limits that people consider. Things like the equilateral limit, where all sides are equal, or of big interest to us will be the squeeze limit, in which one of the sides is much smaller than the other two. And we already know that Planck has put constraints on this, which are pretty good, but they are a bit far. They are still one or two orders of magnitude far from the physically interesting region, which would be so-called FNL order 1, the amplitude of this order 1. Now, can future surveys improve on this? Well, it depends. There are several works studying whether the future surveys will be able to improve on this. And there is still not a complete analysis, but it seems that it will be very difficult to improve on Planck for configurations away from the squeeze limit, simply because the nonlinear growth of gravity generates a signal. It generates a bispectrum, so it's very hard to tell a primordial three-point function apart from this three-point function generated by gravity. But in the squeeze limit, there is a divergence that we will talk about in the primordial bispectrum that cannot be generated by any astrophysics. And so that makes it that the squeeze limit is very solid, and it can be separated from nonlinear growth in a very solid way. And as we will see, it's also very physically interesting. So we are lucky, actually, that we have hopes to improve on the squeeze limit, because on the squeeze limit of the primordial three-point function, because there have been several works that studied that showed that if inflation is single field, so if there is only one light field, and of course there can be many other fields. I mean, nature has more than one particle, but you can ignore all the rest. You can integrate them out, and there is only one light degree of freedom. Then in the limit in which one of the momenta, so in the squeeze limit of the spectrum, goes to zero, this it has a characteristic divergence that cannot be stronger than 1 over q. Instead, if it's multi-field or even some intermediate behaviors, it can have a stronger behavior. So in a very model-independent way, we can look at this divergence. We can look for this divergence, and if we find it, we have detected new particles. We have detected new physics. So that's very interesting. And notice that I'm insisting on the divergence because that's the model-independent part. Of course, when you constrain local non-Gaussianity, which has a similar type of divergence as multi-field inflation, but away from the squeeze limit, it's a bit artificial in the sense you can easily write a multi-field model which can give you a completely different three-point function from the local non-Gaussianity away from the squeeze limit. So the model-independent information is in the squeeze limit. It's in this divergence. So we are looking for this divergence. And more recently, other people have studied spins with higher fields, and it seems also in the squeeze limit there is a characteristic angle dependence between the momentum going to zero and the other momenta that depends on the spin of these additional fields. So you can have even more information about this new physics. And so can this be observed? So already Planck put constraints. If you take into account that the constraints that they cite are 1 sigma, the constraints are FNL of order 10, while a natural model of multi-field inflation would give you FNL of order 1. So we're still at least an order of magnitude away from the physically interesting region. And maybe we can improve with the large-scale structure, where we look at galaxy number density. And of course, using the Poisson equation naively, the galaxy number density is proportional to the matter density. Galaxies form where the gravitational potential is where matter is dominates the gravitational potential. So galaxies tend to form where there is more matter, and this goes like the Laplacian of the gravitational potential. So the divergence I'm talking about is a correlation between the galaxy, would show up as a correlation between the galaxy number density and a long wavelength, so zero momentum, squeeze limit, a long wavelength gravitational potential. And that's where the famous 1 over k squared comes from. If you have such a correlation, you have a 1 over k squared. And so you can try to measure this in 2 ways, either by looking at the galaxy 2-point function. Halo formation is a very nonlinear process, so if there is a correlation between the long wavelength gravitational potential and the galaxy number density, it would leave a characteristic imprint on the galaxy 2-point function that cannot be generated by any astrophysics, because astrophysics is local and the gravitational potential is local and approximately Newtonian, so the gravitational potential in Newtonian physics you can always set it to 0, so you cannot have such a correlation. You can also show this in GR, but the intuition is the same. Or you can look at directly at the 3-point function. Now the 2-point function is very promising, but it has a problem that the amplitude of this effect depends on your biasing, on your halo formation. So you have additional free parameters that you cannot disentangle from the value of FNL. So if you want to disentangle it, you need also the galaxy 3-point function. So let's look at the galaxy 3-point function. So let's see what kind of signal can be induced by gravity that can contaminate this that can contaminate the primordial signal. So let's start at 3 level. So imagine that this is my observed galaxy number density, which is given by some initial value plus additional effects. So this initial value, of course, has to be corrected by relativity. So I'm being very schematic here. I'm not doing the computation, but in GR, you will get in this kind of relation, you generically get terms that go like the gravitational potential itself, simply due to projection effects, geometrical effects. And at second order, you have some Newtonian F2, some Newtonian nonlinear kernel times density squared. This is a convolution in Fourier space, but I'm being schematic. And you will also have relativistic corrections to this, which generically, due to geometric effects, projection effects, can also depend on the gravitational potential. Now, let's see how this affects the bispectrum, especially in the squeeze limit. So if I plug this downstairs, the 3-level bispectrum is given by the nonlinear evolution. The linear evolution has no bispectrum, of course. And in particular, in the relativistic terms contribute, the linear relativistic term gives this contribution. All these contributions are coming from the nonlinear behavior of the short wavelength modes coupled with the long wavelength mode. So here, this is a long wavelength mode that I can take approximately linear. I'm taking it linear in this scheme. And these are nonlinear, so I'm taking the F2 for them. And when I correct the linear expression for the long wavelength mode, I get this term. But if I also include the relativistic corrections to the short wavelength modes, I get this term. And this term is of the same order of magnitude as this one. So a bit counterintuitively, the relativistic corrections to the short wavelength modes are important, which is a bit counterintuitive because you have the intuition that GR effects are only important at large scales. While here, the relativistic effects at short scales are as important as the large scale relativistic effects, and this is because the bispectrum is testing precisely the coupling between scales, and you're coupling the short scales with a long scale where you cannot ignore, so the bispectrum doesn't have a single scale. And in the squeeze limit, this becomes really important because the short scales can be very nonlinear, and the large scale can be relativistic. So then you have to do a calculation which is both nonlinear and relativistic. There is no way around it. And now let's go to higher order. So let's include the cubic term. And if to be complete for the bispectrum, you also need to include the quartic term, but I'm just being schematic, comparing the order of magnitude of different terms. And this F3 is the Newtonian cubic term, which contributes in this way to the bispectrum. This is called a loop because you have an integral. And the relativistic correction to the long wavelength mode corrects this loop, of course. But then you also have a contribution to the loop from the relativistic correction to the cubic loop. And this relativistic correction will be so the ratio between the Newtonian 3-level and 1 loop is as big or small as the ratio between the relativistic 3-level and 1 loop. And so if you want to go to 1 loop and be consistent, you cannot ignore this. And moreover, we will see that the size of these effects is generically of the order of FNL1, so of the same order as the physically interesting region that you want. Now, in the very squeeze limit, so you can when the long wavelength mode is outside of the horizon, you can do this calculation simply by a change of coordinates, and we did this in this paper. We get indeed that the GR FNL is of order 1, and but it would be nice to have a more explicit calculation that you can also use inside the horizon. So we set out to do this in this paper with Lina Castiblanco, Radovan Ganugi, and Clément Stahl. And so we want to do the one loop bispectrum in GR for the reasons that I just explained. And it looks like an almost impossible calculation. You have to go to 4th order in perturbation theory, and already at 2nd order, it's extremely difficult. But we can follow the spirit of these papers here, so the spirit of this paper and the formalism of these two papers, and consider only the leading relativistic corrections. What do I mean by that? So if you think about it, the metric perturbations are always small. Think, for example, in Newtonian linear gauge, Poisson gauge, if you want to call it like that. So the metric fluctuations are always small, and velocities, so they are always of the order 10 to -5, unless I go near a black hole or a neutron star, but that's of course outside of the scope of this calculation. And velocities are also always small. They are of the order of 10 to the -3 at most. So the metric is always weakly perturbed. So we can take a weak field expansion in which we take the metric to always be small, even if density can become very nonlinear. If I take the Poisson equation and plug numbers, even if phi is small, density contrast can easily be of order 1. And so in this way, we can write by expanding the Einstein's equations and the stress energy conservation equation, we can write equations which are fully nonlinear in delta, but perturbative in phi and velocity, simply because if you think about it in the Einstein equations, you only have a few terms with second derivatives, so a few terms that derivatives so we take derivatives to be large, such that delta can be order 1, but we take phi and velocity to be small, so in the Einstein equation, you only have a finite number of derivatives, so you can write equations which are fully nonlinear in delta, but perturbative in phi and b. And for simplicity, we take the universe to be approximately Einstein de Sitter. And of course, Other groups have also done analytical calculations in this approach. So after our papers, Didio and Beutler put out a work where they work in the same line, and but they do it for the power spectrum. However, since they are going to a lower order in perturbation theory, they managed to include the photon propagation, which we haven't done yet. Now, so we managed to write these fully nonlinear equations, which are, you can write in terms of the velocity divergence, which is called theta in the large scale structure. You can write it as the usual Newtonian equations, plus some relativistic effects that they are long terms. I won't show them to you, but you can take them as sources for these additional sources for these equations, which are suppressed by derivatives. And these are just the usual nonlinearities. And these equations, just as in the Newtonian case, are fully nonlinear. They are just expanded in the smallness of the metric perturbations and the velocity. They are fully nonlinear in delta. And but also Newtonianly, you need to solve these equations perturbatively. This is what we do. So we just do a perturbative solution, and what we get is an expansion in kernels where we have the Newtonian kernel plus a relativistic correction. So this is our relativistic correction, highlighted. And I won't show you the calculation because, of course, it can be very boring, but we found a couple of things which are different from the usual Newtonian perturbation theory. One is that you have to be careful with your initial conditions. So the generic solution to these equations for delta will be the solution to the homogeneous equation, of which we only take the growing mode, as is usual, plus some term given by your source, where you also have your relativistic sources. And of course, this coefficient C plus depends on your initial conditions. So what you do Newtonianly is that you fix C plus using the linear initial conditions for delta, because nonlinearities are small at the initial time, but being more careful, since we want to compute small effects, because we are computing relativistic effects, we have to be more careful. And so why can you ignore the second order effects? Why are nonlinearities small at the initial time, even if they are large now? That's simply because nonlinearities grow like a squared, right? So if I go back in time, they decay towards the past. So they are very small at the initial time, and you can ignore them Newtonianly. And let's estimate by counting powers, since we are, for simplicity, in Einstein de Sitter, let's estimate how big these second order equations are in our approximation. So this a squared is 1 over a squared h to the fourth in Einstein de Sitter. And so when I plug in a typical scale, like the typical terms that you will get, this will need to be multiplied by a k to the fourth. So this is very suppressed by derivatives. Right? So it's very, when I put phi squared here, compared to the linear solution, is suppressed by ah over k squared. Yeah. So now let's so in Newtonian theory, if you wanted to keep this, it's inconsistent because then you would have to also keep relativity. Now let's look at the relativistic second order kernel. The relativistic second order kernel has an additional power of a squared h squared. You can get this by power counting in Einstein de Sitter. And so your relativistic corrections, if this go like a, the same power as the linear solution. So they don't grow in time. This also means that they are fixed by your initial conditions. So your delta 2, your matter density contrast at second order in the two gauges that we considered grows like a squared simply by power counting in Newtonian theory. So it's fixed by your initial conditions. And so you cannot, so you have, if you want to compute the second order bispectrum, you have to start by plugging initial conditions at second order. At higher orders, your initial conditions can be ignored because second-order kernel, it's because higher-order kernels will go with higher powers of A, so your initial conditions can be ignored, at least in the approximation that we are doing. We are only keeping subleading relativistic terms. If you're in full GR, your F3 would also have an important contribution from your initial conditions, so then you would have to compute your initial conditions at the order at which you do your perturbation theory. And your initial conditions can, for example, come from the nonlinear evolution of the fluid, etc., that you can compute in codes by Mond, and of course, some of the first groups that highlighted this was this group here. Another difference that we found is that you have to renormalize your background. Let me say what I mean with this. Consider the second order expansion for your density contrast and take the expectation value, you get this. In Newtonian gravity, there is no problem with that because the second order kernel, as the two arguments of the kernel go equal and opposite, goes to 0 quadratically. So the expectation value goes to 0. So if I imagine that this average, it's an average over the whole volume of the universe, then this goes to 0 very fast. Or even over a large volume, this goes to 0 very fast. But in relativity, this is not the case. The second order kernel goes to a constant. So your average density is different from 0. This means that you have to correct your background. And if we don't do this, our loop integrals, they don't only diverge, but they become exactly infinite. So the whole perturbation theory becomes inconsistent if you don't do this. It's not that you can set a cutoff, etc. They become exactly infinity. They are multiplied by infinite quantities, our loop integrals. You don't notice this at tree level, but when you start writing your loop integrals, they're exactly infinite. So you have to take this into account. So at the same order at which you compute your quantities, you have to renormalize your background. And if you include this as part of a correction to your background density, then the integrals are well behaved. So we have to slightly change our background density. And the change is very small. It's over the order of 10 to the minus 5. And similarly, we have that the expectation value of the Bardeen potential is different from 0. Sorry, I forgot to say, we use for what I'm presenting here, we use the Poisson gauge, and we also used the Commuing gauge. The Commuing gauge is the gauge where the constant time hypersurfaces are equal to the constant velocity potential hypersurfaces, which one can choose it also to be the lapse equals to 1, so n equals to 1. And the vector part of the space metric is equal to 0. So it's not synchronous in the sense that the shift is different from 0, because we rather try to make the space metric as simple as possible in this gauge. And it's a very common gauge in inflation. It's very simple in other contexts. But in Newtonian gauge, you can do the same analysis in the Commuing gauge, but in Newtonian gauge, we get the expectation value of the 0 component is different from 0, but you can renormalize this by including a small non-adiabatic pressure that was first pointed out in this paper, and this issue that you get non-zero expectation values of gravitational potentials was first noticed in this paper here. And of course, there's a large literature even before this paper here that considered back reaction. So I'm just citing the papers that I'm more familiar with. Now, what do we get? So I'm going to talk about Commuing gauge because we actually get the smallest effect in Commuing gauge. Of course, this is the bispectrum for the matter density contrast, so it's a gauge-dependent quantity. And I'm going to show you the results in Commuing gauge, which are actually the smallest effect, but it's still relevant in this gauge. So just to estimate the order of magnitude that we are talking about, whether it makes sense to go on with this or not. So this plot is a bit messy. It has too many lines. Ignore the blue and the green line. The orange line is the relativity. So the baseline should be the purple line. The purple line is a primordial signal. of FNL1. And as you go to the left in this plot, the bispectrum becomes squeezed with the two other sides equal and set to 0.1 H inverse megaparsec. So the purple line exhibits the characteristic 1 over k squared divergence. You see it here. And it's FNL1. And the orange line is the three-level relativistic effects. And you can see that it has the same 1 over k squared divergence. Moreover, this F2 that is given these relativistic effects, we noticed something that is not very often highlighted in the literature. This F2 coming from the nonlinear initial conditions has exactly the same time dependence as the primordial signal. So it's completely degenerate with the primordial signal. Of course, if you go away from the squeeze limit, they behave very different. They can behave generically very differently. So, but as I said at the beginning, if you go away from the squeeze limit, you no longer have a model-independent statement about inflation. Then, of course, you can become obsessed with the local non-Gaussianity and say that you can tell this apart from the local non-Gaussianity, but this is a bit fake because you can have models of inflation where you modify this the primordial signal away from the squeeze limit. So you don't get information about inflation unless you correct for this signal. And now let's look at the one loop. So the one loop is, as expected, smaller than the three level, but it's also FNL of order 1, as you can see here. And also the resist dependence is the same as the primordial signal. So again, you have to correct for this at one loop if you want to get to the precision of FNL of order 1. Of course, you have to do this for an actual observable, but we are doing the calculation step by step. Each step is a pretty long calculation, so we are doing this step by step. So the next step is biasing. So to consider biasing, it has been discussed very much in the literature. I don't have space to cite all these papers. The groupings, so you, for example, and has already done many works on this. They're very interesting, but I just want to focus on a very specific discussion. So if we consider halo formation, it's a local process. So it would be better to describe it in some local coordinates. So central. So this image here is some geodesic of an observer in blue, matter infalling in black, and some frame of reference that I choose in red, just to symbolize that ideally one should choose a frame of reference close to the observer that moves with the observer. So ideally, one would describe this with local coordinates, but it's not very clear. I don't know of any explicit calculation that computes that extends these Fermi coordinates or these local coordinates very far from the observer geodesic, such that you can compute correlation functions, for example, of mildly squeezed triangles. For very squeezed triangles, this can be very useful because you can consider the coupling with a very long wavelength mode. But we want to consider generic bispectra. So a way to solve this issue was done in this recent paper here, well, somewhat recent paper here, where they work in synchronous gauge. So the synchronous gauge has the advantage that the coordinate time is equal to the co-moving time of each observer. So that's very useful because then at least you don't have gauge issues. Your clock is well defined. And you can also subtract unphysical couplings with the long wavelength mode by using the same the exact same argument as the large-scale structure consistency relation, which they write down in synchronous gauge. That's very interesting and it works. However, in our case, we want to go to fourth order in the weak field approximation, and there we cannot use the synchronous gauge. And the reason is very simple. The synchronous gauge is a Lagrangian gauge. The for velocity is by definition 0. The space component of the for velocity is by definition 0. So it's the particles move with the coordinates. It's a Lagrangian gauge. So all your information on large-scale structure is contained in your space metric. So the metric, even in the Newtonian limit, is large. It's not a small correction to the Minkowski metric. Even in the Newtonian limit, the metric is very large because you put all your information about structure inside your coordinates. So that's good and it's consistent, as we know. You can do Lagrangian perturbation theory without any problem, but you cannot do the weak field approximation. And of course, there is probably some way to do an approximation around Newtonian Lagrangian theory, but that developing it from scratch would be just too much work. So we took a different approach. So we cannot, for our purposes, we cannot use the synchronous gauge. So what we do is we take a constant observer time hypersurface. So if you will, a constant time hypersurface in synchronous gauge, which is the same as constant observer time. And we describe, and we write down a bias expansion in geometric quantities such that this is independent of gauge. And then we write down these quantities in the gauge in which we are interested in. And the quantities we take for this expansion is the three-dimensional curvature of the surface, which has the same information as the matter density. Actually, we take the second for the expansion. And the extrinsic curvature of the hypersurface. Interestingly, the extrinsic curvature of the hypersurface has the same information in the Newtonian limit as second derivatives of the gravitational potential, which is how the Newtonian bias expansion is usually written. You can have many other terms describing geometrically this hypersurface, but as we discussed in the paper with Juan Calles, Lina Castiblanco, and Clément Stahl, these other terms, for example, you can consider terms containing the tensor modes, Weil tensor, etc. But all these other terms are the differences at each order in perturbation theory with these terms is suppressed by h over k, suppressed with respect to what we have. So we do this, we write down a generic expansion, and we take a Lagrangian approach, meaning we describe bias for an initial overdensity at some initial time. At this initial time, simply because it's simple, at an initial time, the commutative gauge in which we work and the synchronous gauge coincide. So we don't have to write down these quantities in a very complicated way. We can just look at them at the initial time, and then we evolve in time. This is similar to what was done in this paper here. And again, I won't show you the calculation. You can look at the paper, but I want just to point out that an interesting difference with the Newtonian calculation. So in the Newtonian calculation, and also for us, when you consider an operator, you have to be careful in this bias expansion at some initial time, because the operator has to be renormalized. What do I mean by that? Take the expectation value of this expression. So yeah, so the operator delta squared has the Newtonian term, which is the upper one. But since at the initial conditions, I cannot ignore F2, I will also get a relativistic correction. And if I do things geometrically, I was explaining, and you can get terms also for the other relativistic corrections also for all the other bias operators. So now take the expectation value of this quantity, and you get you simply get this after you renormalize the background, of course, as we discussed before. And so you get that the expectation value of this is non-zero. This also in the Newtonian case, actually, they come from the first line. This comes from the first line. The second one disappears after background renormalization. And so you get a non-zero expectation value that also depends on the scale on which you smooth your overdensities, which is kind of ugly because you don't want your bias expansion to depend on some arbitrary cutoff that you chose. But as is widely discussed in the literature, you can simply correct for this issue by subtracting this expectation value. So your actual operator in the bias expansion should be this. This is the so-called renormalized bias operator. Now let's look at, also in the Newtonian case, you have to consider correlations between your operator and long wavelength mode. So let's consider a correlation with a long wavelength mode of this kind. And if you get something non-zero and cutoff dependent, you should also subtract it, because this is some artificial cutoff dependence. So you have to redefine your operator such that you subtract this. And when I consider the correlation with the long wavelength mode, in the Newtonian case, for this quadratic operator, it's 0. For other operators, it's not, and you have to be careful and subtract appropriately. But for this operator, it's 0. It's 0. For us, also, for example, in the presence of primordial non-Gaussianity, this is non-zero also in the Newtonian case, and you have to renormalize it appropriately. For us, even with Gaussian initial conditions, this is non-zero. With some integrals, I'm just giving them names. The sigma minus 2 is just some integral. And again, I have a dependence on the cutoff. So I have to renormalize. My actual operator is this one. But this term highlighted in red looks a bit problematic because it goes like 1 over k squared. So when I consider it as an operator in my bias expansion, it's an operator proportional to the metric fluctuation, which is the kind of operators that you have to include, for example, if you have primordial non-Gaussianity. So do we have to include this operator? If this were the case, then your bias expansion, for example, you would get a scale-dependent bias with an arbitrary coefficient similar to what you get in primordial non-Gaussianity, and it would be very hard to tell primordial non-Gaussianity apart from this relativistic contribution. It would be impossible, because in your bias expansion, you need, when you renormalize with some new operator, you need to include an arbitrary coefficient in your bias expansion, and so then you have an arbitrary coefficient. So you cannot. It really becomes completely degenerate, and you cannot measure primordial non-Gaussianity. However, this is not the case. We don't need a new operator, because this object, so this red term combines with this blue term. Let me consider them together. I'm writing them here. And these integrals, sigma, are cut off at some coordinate momentum, lambda. So I have some coordinates put here in green, this is just a schematic representation. But actually, these coordinates are different from your observer frame, which actually you should define your bias expansion with respect to a local observer. So when you, for example, if you take one of these integrals, if you take the variance, and instead of cutting it off at some coordinate momentum, you should cut it off. You should compute it at some local momentum, at some momentum in the observer's frame. And that was, as was pointed out in this paper here, when you do this, you get that the physical variance is given by this expression. So it's exactly this combination that I have here. So the only operator I need is B2 star to renormalize is B2 star times the physical variance. So I don't need new operators in my bias expansion. And we see this. So this was not seen before in this language of bias renormalization. And we see this for every operator. For every operator, we have terms that contain the curvature fluctuation. But when you renormalize, it seems that you need to include them. But there is always the exact same combination with the variance that gives you the physical variance, the local physical variance. So, which is kind of nice. It's a consistent framework. In very complex fourth order bias operators, we get always exactly this combination that when a dangerous term appears. So we don't need a new coefficients in our bias expansion. And so that's all I wanted to tell you today. Thank you for listening. I wanted so the next step we have to take is to compute also the photon propagation in order to get the final observable. We are doing this, but we have a problem. Maybe you guys can help. For us, it's very difficult to define the volume perturbations at fourth order, because when we want to consider an actual observable quantity, if you're an astrophysicist, when you look at the sky, you take averages to define this galaxy number density, this continuous field out of a discrete field. You take a region of the sky and average in a redshift bin. Now, so you have to average over this volume. What is usually done in the literature is to average over a volume for a co-moving surface, a surface that is moving with the galaxies. But this is not what the astrophysicist would measure. The astrophysicist would measure a volume on the light cone. And my question is, what do you think about this? Does this sound correct? Because I haven't seen it discussed in the literature. And if you know of any literature that does discuss it, please tell me. Thank you for listening.